Hi guys, thank you for being here. Welcome to our Exam 5 review session. Can everyone hear me well? Okay, awesome. So if you haven't done so already, as you come in, please mute your microphone. And if you don't know already, this session will be recorded and uploaded on the Peer Tutoring YouTube channel. So if you need to leave early or anything, that's okay, it'll be on the YouTube channel. Yeah, so I'm Aditi. I'll be doing the first half of this exam review, and then after that, Yasir will take over. If you want to say hello really quick.
Hi, I'm Yasser. I'll be doing the second part of the session. Yeah.
Okay, cool. Let's get started. Okay, so we're going to start off by talking about enthalpy. So enthalpy is the heat content of a system at constant pressure. And then if we're talking about enthalpy change or delta H, that's going to be where we measure the change in potential energy of the bond. So we can think about this in terms of exothermic and endothermic reactions. So when we have an exothermic reaction, you know that we're going from high energy to low energy. So if we're starting off with high energy, we are going to have weaker bonds because they're going to be high energy, they're going to be a little more unstable, and then we're going to be making stronger bonds that are going to be more stable and at lower energy. And then the opposite will be true for endothermic reactions. We'll be going from low energy to high energy. So we're starting off with stable and strong bonds, and we're going to be making weaker bonds. Okay, so y'all know that there's plenty of ways to calculate delta H. The first one that we're going to talk about is using specific heat. So the equation that we use is Q equals MCAT. And so C is what the specific heat is. And the specific heat is the heat required to raise 1 gram of a substance by 1 degree Celsius. So metals generally have a low specific heat. And what this means is that it doesn't take a lot of energy to raise the temperature of a metal. So that's why we use metals for cooking and things like that. Whereas materials like water, they have a higher specific heat, which means that it takes a lot of energy for water to heat up. So yeah, that's the equation right there, Q equals MCAT. Make sure you know all the units for it. And yeah. Okay, so the next one is calorimetry. The basic principle of calorimetry is that heat lost equals heat gained. So the basic example is the coffee cup. So in the coffee cup, you have your cup, and assuming there's no heat loss, there's going to be a reaction going on inside the coffee cup, and whatever heat that's lost by the reaction is gained by the surroundings. Yeah, so if you have an exothermic reaction happening, then the heat is gained by the calorimeter, whereas if it's endothermic, then the heat is gained by the reaction. Okay, so these are the main factors that affect your delta H. The first one is the direction of a reaction. So if you have a reaction with a certain delta H, you can just flip the reaction and your delta H is just going to be the opposite sign. So in the A plus B gives C, we have plus 20, we flip the reaction, it becomes negative 20 kilojoules per mole. The next one is the amounts of substance reacting. If we have a reaction and we double each of the moles in the reaction, then to find the new delta H, you just multiply the original delta H to find the new delta H. And then the third thing to remember is that your states of matter need to be the same in order for these rules to apply. So if something changes from a solid to a liquid, you can no longer use these rules because it's not the exact same reaction. Okay, next up we have Hess's law. So Hess's law is where they give you multiple equations with different delta H's, and you're told to find the final delta H of a certain equation. So the way that we do this is we know that the total enthalpy change for the reaction is going to be the sum of all the changes. So when two or more reactions are added together, the new reaction's enthalpy will be the sum of the previous reactions. And this works because enthalpy is a state function. So a state function means that only the initial and final states matter. It doesn't really matter how we get to the final state. We can do it all together in one equation. We can do it in 2 or 3 or 4. It doesn't matter how many steps. But as long as we have the same initial and final states, it doesn't matter. So that's why Hess's law works. Okay, and this is just a quick example of Hess's law. You can see that we found a final equation by canceling out the reactants and products that we don't need, and we just added together the two delta H's to find the final delta H. Okay, so enthalpy of formation. This is the enthalpy change for the formation of 1 mole of a compound from its corresponding element. So if we look at this equation, the H2 plus 1/2 O2 gives H2O, that's an example of an enthalpy of formation equation. So make sure when you're writing these equations, you're never changing the coefficients of the product, like the H2O, because it's an equation to find 1 mole of that final product. Yeah, so I know generally it's like it feels a little weird to use fractions as coefficients, but in this case, like, go ahead and do that. And then when is it 0? Enthalpy of formation is 0 when the element is in its standard state. So for example, O2 is the standard state for oxygen, so enthalpy of formation will be 0 for that. And that also applies to all of the diatomic molecules. So if you don't know those, go ahead and review them. Okay, and then the last way to calculate delta H that I'm going to talk about is using the standard heats of formation. The equation for this is pretty simple, where you do the heat of formations of the products minus the heat of formation of the reactants. And the only thing you need to really watch out for is to make sure you multiply all of your delta H's by the corresponding coefficients on the equation that's given to you.
Okay, so I'm going to be going over gas laws and gas law equations and those kinds of concepts. So you have the individual gas laws. I'm sure you guys have seen these. They tell you the relationship between two variables, like pressure or volume or temperature. So in general, your gas laws equations, they basically just show you the relationship between pressure, volume, and temperature. And then you have your ideal gas law right here, Pivnert. So let me ask you guys this. So in Pivnert, what's the R? Just answer in the chat. Yeah, it's the ideal gas constant, right? And so the gas constant 0.08206, it's in like the units for the gas constant are liters atmospheres over moles Kelvin. So that's why whenever you're using the ideal gas law, you want to use those. Yeah, exactly, right? You want to use those units exactly. Yeah, so this is just like a brief summary. We're going to go over each one of these laws in a little more detail in the next few slides. So, all right, so Boyle's law, right? And I find that the easiest way to like really understand these laws is to look at real world examples. So I have one for Boyle's law right here. So what would happen to the volume of a balloon if you were to increase the surrounding pressure by squeezing the balloon from all sides? So basically you have a balloon, you're squeezing it from all sides for whatever reason, what would happen to the volume? Would it increase? Would it decrease? Yeah, the volume would decrease, right? Because you're applying pressure, and that's what Boyle's law basically shows us. It shows us that volume and pressure have an inverse relationship to where if you increase one, the other decreases, and vice versa. And you can write Boyle's law as by multiplying the pressure by the volume, and you would get a constant, assuming that you are at a constant temperature. So what that means is that at a constant temperature, if you multiply the pressure and the volume, you would get the same constant. So that's why we can use this equation right here. So P1 V1 equals P2 V2 at constant temperature, which tells us that it's a way for us to figure out how the volume or pressure would change if we change the pressure or volume, right? So if we increase the pressure, so we have P1 right here, V1 right here. So if we increase the P2 pressure, what would happen to V2? So your final volume, what would happen to it? Yeah, decrease, right? And then back to like the inverse relationship. Cool. Let's move on. All right, Charles' law, it's another one of our laws. So let's look at a real world example. What happens to the tires of your car if you're parked outside in the winter? Like what happens to the volume of your tires, I guess? Yeah, the volume decreases, right? So during freezing winter days, the temperature falls and consequently the volume of your tires also decreases. So Charles' law basically says that under a constant pressure, if you increase the volume, your temperature is also going to increase. If you decrease the volume, um, your temperature is going to also decrease. So that's what this law shows us right here. So you have V1 over T1 equals V2 over T2. So suppose you decrease the value of V2, so you decrease your final volume. What would happen to T2, your final temperature? Yeah, it would also decrease, right? It would decrease so to make sure that both sides of the equation still equal each other. Simple enough. All right, let's move on. All right, Avogadro's law. I think it's the easiest one to comprehend. So you pump air into a ball. So think of it like you're pumping more moles or molecules into a ball. And as a result, what happens to the ball? Like what happens to the volume of the ball? It increases, right? You pump more stuff into the ball, the volume increases. Simple enough. So the official definition, under constant pressure and temperature, there is a direct relationship between the volume and the moles of gas. So if you increase the moles of gas, if you increase the moles of gas, your volume is also going to increase. So that's what this equation shows us right here. And when you divide the volume by the moles, you have a constant number, assuming you're at constant pressure and temperature. So at constant pressure and temperature, we can write this equation to figure out how the change in volume or the change in moles may affect the other variable. Cool? All right. So the combined gas law is essentially a combination of the other three gas laws. And what it tells us is it basically takes into account the relationship between pressure, volume, and temperature. So if you notice in the previous gas laws, you had at least one variable that was constant. For example, in Boyle's law, you had temperature that was constant. However, the combined gas law, it lets you take into account um, like the change in like the volume, for example, while pressure and temperature are increasing or decreasing. And if you'll notice that you can essentially memorize just this equation and you'll have the other three gas laws, right? For example, Boyle's law, we have a constant temperature, right? So at constant temperature, your T1 and T2 are going to be equal to each other. So if you just start off with your combined gas law, you cancel out T1 and T2. All you're left with is this right here, which is Boyle's law. Right? And it just shows the relationship between pressure and volume at constant temperature. So make sure you memorize this equation right here. Okay. Yeah, just memorize this equation right here. Very important stuff. All right, cool. All right, and so now we're back to our ideal gas law, and it shows us the relationship between pressure, temperature, and the volume of a gas, as well as the moles. Are we taking into account the number of moles in the combined gas law? So usually the combined gas law is written like this. So it doesn't have moles, but usually moles are constant, right? Unless you're adding something. Uh, Generally in a question, your moles are going to be constant because you're not really adding anything. Yeah. All right. So the ideal gas law describes, but if, okay, let me go back. So if you were to add moles, that would be right here. But since they're constant, they just cancel out. Cool. All right. So the ideal gas law, Pivnert, you guys know this. So let's just go over the units that we use in our ideal gas law equation. So P is our pressure. It's always in atmosphere. V is our volume. It's in liters. N is moles. R is our gas constant. And then T is temperature in Kelvin, right? Make sure whenever you're using this equation, you always convert to Kelvin. Now, the reason that we have to use these units in our ideal gas law is because our constant, the R constant, is in those units. If you want, if the question gave you different units for pressure, for example, you would just convert back to atmospheres or change your gas constant. I would recommend not changing your gas constant, just change the variable itself. All right. Okay. Another important thing to understand is the difference between real and ideal gases, right? So what is an ideal gas? An ideal gas is something that it's like a hypothetical gas that doesn't actually exist in the real world, right? We just assume that something's an ideal gas to make the calculations easier for the most part, right? So ideal gases have certain properties that we assume to be true. One of them being that there are no intermolecular forces present. In real gases, obviously, there are intermolecular forces present. We also assume that ideal gases do not have a definite volume, so we assume that the gas particles themselves do not have a volume. When in real life, obviously, gases, the particles do have volume. We assume that the collisions are elastic. What that means is that when gas particles collide, they do not lose any energy. Uh, However, in real life, that's not true. And the kinetic energy is constant because the elastics are are elastic, or the collisions are elastic. So another important thing just to keep in mind is that real gases behave most like ideal gases at low pressures and high temperatures. Can anybody guess why that is? Just guess. So why do real gases behave like ideal gases at low pressure and high temperature? Yeah, so like Joanne said, at low pressures and high temperatures, they're farther apart, right? So what that means is that the particles are so far apart that the space between them is so large that the actual volume of the particles is not significant, right? And that's where our assumption of gas particles not having a definite volume comes in. And then at high temperatures, they have high kinetic energy, so the potential energy of our IMFs are relatively insignificant, right? And here's where the no IMF forces comes in. Cool. All right. Okay, so with our ideal gas laws and just gas laws in general, there's a few equations or like a few types of questions that can be a little tricky to answer. And one of those questions is when you're calculating for density, right? If a question asks you to calculate for density, the easiest way to do it would be first. So here's our ideal gas equation, right? You have PV equals nRT. Now we know that density is calculated in mass by mass over volume. So the units for that would be grams per liters, right? However, in our ideal gas equation, we do not have mass. So first you want to transform this equation to look as close to our density equation as possible. So the first thing you would do is solve for N over V. And the units for that would be moles over liters, which is very similar to grams over liter, but not really. Right, and you would get P over RT. Once you calculate for moles over liters, so which is this thing right here, and you plug in your values per P, R, and T, you get moles over liters, right? And then in order to calculate for density, you're going to use your molar mass and divide your answer by divide your moles over liters, not divide, multiply your moles over liters by the molar mass to get grams over liters in order to calculate for density. All right, and there's a question in the practice questions that we have at the end that asks for density. So yeah. All right, and one of the last things that I want to go over is partial pressure. Partial pressures basically make up the total pressure of whatever container you have. So in order to calculate for the total pressure, what you would do is you would add up all the partial pressures of each individual gas. You can also use mole fractions to calculate for partial pressure. So if you have the total pressure of something and you know the mole fraction for that substance, whatever it might be, so suppose it's oxygen gas, if you know the mole fraction for oxygen gas, you can just multiply by the total pressure in order to find the partial pressure of oxygen gas. Cool. Right. And there's some questions on this as well. All right, last thing that I want to go over is kinetic energy. So at a constant temperature, do you guys think oxygen or nitrogen has a higher kinetic energy? So so they would have the same kinetic energy. I think some people might have answered nitrogen because you're thinking more of average velocity, right? So although all of the gases at the same temperature are going to have the same kinetic energy, they are not going to have the same average velocity because you have to take into account their mass. So when you have a higher mass, you're going to have, at a higher mass, you're going to have a lower velocity. And but at the same, if they're at the same temperature, they're going to have the same kinetic energy. And I wrote the formula for kinetic energy. You do not need to know this formula, but it helps you visualize why a higher mass results in a lower average velocity. All right, and effusion rate is also very similar to this whole concept. So it refers to the movement of gas particles through a small hole. So for example, what you need to know is that at a higher velocity, your effusion rate is going to be higher. And it looks like that is all we have for you in terms of the content review. And let me see what questions. Yeah, so the effusion rate does depend on the molar mass, right? So even if two things are at the same temperature, they have the same kinetic energy, however, they are going to have different effusion rates depending on the molar mass. ERMS. URMS. I am not sure. Let me check. And okay, so just hold on tight and we're gonna split up into breakout rooms.
Hi guys, give me 1 second to get the questions up on the screen and then we'll get started with the problem. Okay, so number one, let's get started. It says a 43-gram sample of an unknown metal is heated with 950 joules. The temperature changes from 25 degrees Celsius to 70 degrees Celsius. What is the specific heat of this unknown metal? So where would y'all start with this problem? Okay, yeah, that's a good place to start. Finding the temperature change. So we're going from 70 to 25. So what is that temperature change? Yeah, it's going to be 45 degrees Celsius. Okay, so then what would you do next now that we have the temperature change? So not quite Pivner. This problem is asking for a specific heat. So which formula contains specific heat? Y'all are thinking of gas laws right now. But this is the solid, this is a metal. Yeah, so it's Q equals MCAT that we're using. There you go. Okay, so what are we gonna plug in for Q? $950. So Q is where you put the energy, and the Q units are gonna be in joules, which is already given to you. So we're gonna do 950 joules equals, and then what are we gonna plug in for the M? 43 grams. And what does C stand for? Specific heat. So that's what we're solving for. So we just leave that as is for now. And then the change in temperature, you guys already found out that's going to be 45. So then what's the final specific heat that we get? Zero 0.491. Oh, sorry, that's a little messy. But it says 0.491. And what is the units for specific heat? Perfect. Joules per gram Celsius. And it's important to know those units just because when you're using the Q equals MCAT formula, you want to make sure all of your variables are in the right units. So if you just know the units for specific heat, then you know the units for everything else in the formula. Any questions on number one? If not, then we can go ahead and do number 2. So number 2 says, given the delta H for the following equation, and then it gives you the equation with the delta H of negative 354 kilojoules per mole, determine the delta H for the following reactions. So look at the equation in letter A. So what do you notice about that equation compared to the one given? It's reversed. So what does that do to the delta H? Yeah, it's going to turn positive. So right now it's negative 354 kilojoules per mole. When we flip our equation, it's going to flip the sign on delta H because we're doing the backwards reaction. And our new delta H is going to be 354 kilojoules per mole, like you said. Okay, what about B? How does B compare to the original equation? Times 3, correct. So all of the coefficients are multiplied by 3. What does that do to the delta H? It triples it. So what's our new delta H going to be when we triple it? Yes, it's going to be negative 1,062 kilojoules per mole. And then last one, C. How does C compare to our original equation? Yeah, that was fast. Reversed and multiplied by 2. So what does that do to our delta H? Oh, you guys already have answers. So like you said, to the delta H, it's going to flip the sign, and then we're going to multiply it by 2, just like all the coefficients did. So our new delta H is 708 kilojoules per mole. Perfect. Yeah. That's it for number 2. Make sure when you're doing these problems, you're looking at states of matters. They have to all be the same compared to the original equation for this to work. Otherwise, you're not able to find the new delta H's because it's not the same reaction. Okay. So let's do number 3. 3 is a Hess's law problem. So it says given and then gives you 3 equations with their corresponding delta H's, and it says calculate the delta H in kilojoules per mole for the following reactions. It gives you the reaction. So how do you guys approach these problems? What's the first thing? If we look at the first equation that's given, what do we need to do to it? Or do we need to do anything to it? Yeah, look for things unique to each equation. That's a great way to put it. I like to start off by looking for things that's only in one equation so that I know which side it needs to be on, what coefficients it needs, or things like that. So you said look at C4H8 first. So C4H8 is in the first equation, correct? So what are we going to do to our first equation? Reverse it, yeah. So when we reverse it, what's it doing to our delta H? Yeah, it's going to turn into positive 7.1. Okay, so then let's look at our next thing. And what's another thing that's unique to the final equation or another molecule? C4H10. So that's in the second equation. Do we need to change anything about it? So we actually don't need to flip it because it's already on the product side in both equations. So y'all are correct to say no, we don't need to change anything about it, and the delta H just remains the same. So now let's look at the final equation. So we have 2H2 plus O2 gives 2H2O. What do we need to do to this equation? Reverse and divide by 2. And how do you know to do that? Yeah, so we need H2O alone on the reactant side. So you know to flip it and divide by 2. So we get H2O gives 2H2 plus, oh sorry, not 2H2O. 1H2 and 1/2 O2. And then what's our new delta H? It's 241.8, yeah. So all we did was flip it, so it turned into positive 483.6, and then just divide that number by 2. Yeah. Okay, so is everything where we want it at this point? Yeah, and then what are the things that we need to cancel out? Yeah, everything except the 3 in the final equation. So that's your H2 and our O2. So if we count out the H2s on our reactant side, then we have 5. And then if we count out the H2s in the product side, then we also have 5. So that means that they cancel out perfectly. And then the same thing goes for O2, where we have 1/2 O2 on the reactants and product side, so they cancel out, sorry. So now what's the last thing that we need to do to finish off this problem? Add all of the delta H's, yes. So can y'all go ahead and add those all together and tell me what you get? Negative 43.9 kilojoules per mole. Yeah, that's correct. Perfect. Any questions with Hess's law? If not, then we can go ahead and do heat of formation equations. Okay, so okay, so let's start with number 4. A says C2H6 gas. So how do we write heat of formation equations? What's going to go on our product side? Yeah, so we're going to use composite elements for the reactant side in order to make the product, which is whatever they're asking us. So I like to just draw the arrow and go ahead and write in what the product is going to be, because we know that based on what it's asking in the problem. So we have C2H6, and it's a gas. So then On the reactant side, like you said, we're going to use our composite elements or the elements in their standard states to write the reactant. So, like you said, it's going to be carbon and hydrogen because that's what's in our product. So, let's write carbon. And what's the standard state for carbon? Yeah, carbon's going to be a solid. And then what about hydrogen? What's the standard state? Yeah, it's going to be a gas, and yeah, H2. So remember your diatomic molecules, they're always going to exist in pairs and they're always going to be gases. So if you don't know, like the mnemonic for the diatomic molecules is Hofsprinkle. So it just spells out the diatomics. Definitely memorize those before the test. So yeah, we have carbon and H2 to give C2H6. And then what's the last thing we need to do? Oh, it's Hofsprinkles. Hof, hold on, let me write it. Like that. It's hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Okay, so back to A, what's the last thing we need to do to finish off this equation? Balance. What coefficient should be on the carbon? 2. And then what about the hydrogen, or the H2? 3. Yes. Sorry, that's kind of squished, but we have 2 carbons and 3 H2s to give C2H6. When you're doing these, remember to always put your states and matters in there because they're very important. But yeah, that's all for A. Let's do B. So B is CaCO3 solid. Okay, so what are our elements that make up CaCO3? Yes, exactly. So calcium, let's do calcium first. You already said in the chat that calcium is a solid. That's correct. And then what about carbon? We already talked about this, but yes, always break up the polyatomics. Everything's going to be in its standard state. So a polyatomic has bonds within it, and so it's not in its like basic state. So for our carbon, yeah, it's a solid. So carbon's not a diatomic, so it's not going to be C2. Yeah, perfect. So it's going to be carbon solid. And then the last one, oxygen, how is that going to be in its standard state? Yeah, O2 gas. Oxygen is a diatomic. And then last step, how do we balance this equation? What coefficients do we need to add to this equation for it to balance out? Not quite. Remember, you never want to change the coefficients on the product, the CaCO3. You always want to keep that as a 1, even if that means you have to use fractions for the reactant coefficients. So you can use like any fraction that you want for the coefficients of the reactant. But the CaCO3 always has to be 1. Yeah, so on the oxygen, we're going to put a 3/2 because we have 2 oxygens, and multiplying that by 3/2 leaves us with 3 oxygens. And then on the product side, we also have 3 oxygens in calcium carbonate. Yeah, so I know that it like feels kind of funky to use fractions as coefficients in equations, but for heat of formation reactions, that's okay because you always want to be forming 1 mole of your product. Okay, so let's do the last one, N2O4. So what makes up N2O4? Dinitrogen tetraoxide. Yeah, N2 and O2. And what state of matter are these in? Gas. These are both diatomic molecules. And then do we need to add coefficients to this equation? Yeah, we're going to have 2O2. Yeah, so that's it for this one. No fraction coefficients for this one. Yeah, that's it for heat of formation equations. Do y'all have any questions? Okay, then let's do number 5. I believe this is our last problem for enthalpy before we move on to gas laws. Okay, so it says, given the following enthalpies of formation, what is the delta H in kilojoules for this reaction? And it gives you a reaction, and it gives you all of the delta H formations for the compounds. So how do we approach this problem? Which equation are we using? Yes, we're going to do delta H of products delta H formation of products minus delta H formation of reactants. Hopefully you can read that. Sorry, it's a little messy. Okay, so the products are H2O and CO2. So what do we have on the product side of this equation? What numbers? Well, I'm going to do it in like steps. So so what's the delta H formation of the CO2? Yeah, so it's negative 393.5. And we don't actually need to multiply it by 2 because CO2 doesn't have any coefficients on it. So for CO2, we're just multiplying by 1. So we can just leave it as is. And then for H2O, what is going to be the heat of formation for that? that one's going to be negative 241.8 times 2. And the times 2 is because H2O in the equation has a coefficient of 2 on it. So this makes up all of our delta H's of products. And then we're going to subtract from the delta H of the reactants. So first up, we have CH4. Yeah. So y'all said delta H for CH4 is negative 74.8. And yeah, the delta H formation of O2 is 0. So we just do plus 0, or we don't even have to write it in. And you know that because O2 as a gas is in its standard state. So like we talked about in the last problem, when O2 is a gas, it has a delta H formation of 0. So when we do this problem out, what answer do we get? What number do we get? That is correct, negative 802.3 kilojoules per mole. Perfect. Any questions on this problem? If not, then we can go ahead and do gas laws now. Okay, so starting with number 6, it says a 4.4 gram piece of solid CO2 is allowed to vaporize in a balloon. The final volume of the balloon is 1 liter at 300 Kelvin. What is the pressure of this gas? So what equation are we going to be using for this problem? Pfiffner, yes. Okay, so let's go ahead and fill in all the stuff that we know. So pressure. Well, that's going to be what we're looking for, so we don't actually know it. So we can just write in the P. What's the volume that's given? One liter. And then do we have the moles? No, we don't have the moles, but can we find the moles? What can we use to find the moles? Yeah, use molar mass. So it does tell you that you have 4.4 grams of the CO2. So we can use molar mass to convert. So 4.40 grams. And then what's the molar mass of CO2? (44.01), correct. Yeah, so you already solved it out and you got 0.1 moles. Yeah, I also got 0.1, but to be more specific, I'm just going to say 0.099. Okay, so now we can go ahead and plug that into our Pfiffner formula. So we have 0.099 moles. What's our R? 0.08206, and the units are liters per ATM, or liters ATM per mole Kelvin. And then what's the temperature? 300. And it's already in Kelvin, so we don't need to convert it. So we have all the information that we need. Go ahead and solve for pressure and see what you get. .46 ATM. Perfect. That is also what I got. Okay, so let's do number 7. It says a sample of an ideal gas occupies 5 liters at 27 degrees Celsius and 62.5 torr. Calculate the volume the gas would occupy at 177 degrees Celsius and 375 torr. So which equation are we using for this? Yeah, the combined gas law, because it gives pressure, temperature, and liters, and volume, sorry. So the combined gas law is PV over T equals PV over T. Okay, so what's our starting pressure that's given? Yeah, 62.5 torr. What's our starting volume? So if you want to change to ATM, then you can change, but as long as the pressures on both sides of this ratio are equal, so as long as they're both torr in this case, then you're good to just find it that way. Yeah. The exception is with temperature. You can't just have both of them be the same as Celsius, because it doesn't work out that way. You have to have them both in Kelvin at all times. So remember that with your ratios, your pressure units can differ as long as they're differ from ATM as long as they're the same as each other. But with temperature, you always need to have them as Kelvin. Yeah. So I'm just going to keep it at 62.5 torr just because it's easier that way. If you feel more comfortable converting to ATM, that's cool too. I always keep it in liters just because that conversion is really easy, but I don't think it does. I think it has to be just the same on both sides. Yeah, I'm not completely sure on that one, but yeah, I think they can be in like milliliters as long as they're both on the same side. The ones that I know for sure are that pressure can be like in torr as long as they're on the same side, and temperature has to be the Kelvin. Yeah, but with volume, milliliters to liters is an easy enough conversion that I always just go ahead and do it. Okay, so what's our starting volume? Five liters. Yes. And then what's our starting temperature? So 450 is actually our final temperature. Yeah, so our starting temperature is 300.15, which is the 27 degrees Celsius plus 273. And that's going to be equal to, what's our final pressure? $375, and that's also in torr, which matches our initial pressure. And then we're solving for the final volume. And what's our final temperature? Two 273.15 is going to be more accurate for the Kelvin conversion. Yeah. Yeah, 450.15 is our final temperature in Kelvin. Okay, so go ahead and do the math out with this problem and find our final volume. Yeah, 1.25 liters. That's the correct answer. Isha, your answer was really close, so maybe you just hit like a wrong button on the calculator. But yeah, 1.25 is the correct answer. Okay, awesome. Okay, so let's do number 8. 8 says, what is the density of oxygen at 25 degrees Celsius and 4 atm? So for finding density, do y'all remember the like version of the formula that we use for Pivners? Yeah, so okay, so density is equal to mass over volume, which is the grams over volume, or grams over liters, which is what we're trying to find. So when we have Pivners, there's no grams in here, but what we do have is moles, and so we can use that to convert to grams. So the first step is manipulating this equation to where we move the volume to the right side by dividing. So we're going to say pressure equals moles divided by volume times RT. And so this moles divided by volume, what units does that give you? Yeah, so the N over V portion gives you moles divided by liters, and that's super close to this unit, the density unit, which is grams over liters. So let's go ahead and solve for that part. So what's our pressure in this problem? Yeah, we have 4 atm equals, and then we're solving for the moles over volume. What's our gas constant again? And then what's our temperature? Yeah, 298.15. So notice they give you the temperature in Celsius, so we need to convert to Kelvin. There we go. Okay, so then go ahead and solve for the moles over liters value. Yeah, you're correct. 0.163 moles over liters. Okay, so then how do we convert this to grams over liters? Multiplied by molar mass, correct. And molar mass is 32 because it's oxygen gas, and oxygen gas always exists as a diatomic, so it's O2. So you know it's 32 grams per mole. And then what's our final answer? Yeah, 5.23, and we have it in grams per liter. Sorry, not mole. Grams per liter. What's our final answer? Okay. Okay, so number 9 says, which noble gas will have the highest kinetic energy at 300 Kelvin? Do y'all have a guess as to what answer that is? Yeah, they're all the same. So sometimes it gets confusing when problems ask about kinetic energy versus velocity, but remember that the formula for kinetic energy is 1/2 mass times volume squared. And so what that means is as the mass of something increases, the mass of the molecule increases, the volume decreases, but the kinetic energy always stays the same, assuming it's at the same temperature. And yeah, Isha, you're correct. The kinetic energy is staying the same because temperature and kinetic energy are directly proportional. So as long as temperature is staying the same at 300 Kelvin, the kinetic energy is also staying constant. Which is why all of these noble gases have the same kinetic energy at the same temperature. Any questions with that? You're good. Okay, so 10 says, under what conditions does a real gas behave most like an ideal gas? What do y'all think? Yes, perfect. Low pressure and high temperature. So we talked about this in the review portion. Do y'all remember why this is? So when we have oh, there we go. Yeah, so at high temperature and low pressures, the particles can be really far apart. And yeah, so that helps it behave like an ideal gas because the molecules are really far apart. And so any interactions that they may have with each other are just like negligible because they're so far apart. And same with temperature. As you increase temperature, your molecules are moving really fast. And so that again also reduces any of like the intermolecular forces to the point where it's mostly negligible. So low pressure and high temperature. Okay. Any questions so far on anything we've discussed? Okay, cool. Let's do number 11. So 11 says, a student adds 0.1727 grams of an unknown gas to a 125 milliliter flask. The pressure of this gas sample is found to be 0.833 atm at 20 degrees Celsius. Is the gas likely to be methane, nitrogen, oxygen, neon, or argon? So how do y'all think we are going to approach this problem? What are we going to be solving for? Yeah, so we're going to be finding moles by rearranging Pivners. Yeah, so let's go ahead and do that first. What is the pressure that's given to us? .833 atm. What's the volume? It is 125 milliliters, but what are we going to use for equation? Yes, 125 liters. And remember, that's because the units for the R are they have liters in the units. So we're going to have to use liters in the equation. So that's 0.125 liters, and then we have N, which we're solving for, and then what our R is 0.08206. And what's our temperature? Yeah, it's going to be 293 Kelvin. So go ahead and do the math out for this problem and let me know what the moles are. Correct. So it's going to be 0.0043. moles. So then how are we going to use this to determine which of the gas molecules it's going to be? Because all we have right now is moles. Yeah, we're going to find the molar mass using the grams given. So what are the units for molar mass? Yeah, grams per mole. And so we can recreate that by using the grams given to us, which is 0.1727 grams, and divide it by the moles that we just solved for. So 0.0043 mole. And then what do you get? What do we get for molar mass? Yeah, so we get 39.87. And which of the given molecules is that? You got it, it's argon. So we would go to the periodic table and the molar mass is given, and argon matches this molar mass. So the correct answer is argon. Any questions before we move on? Okay, so I'm going to erase the board. Let's see. Number 12 says, name 2 ways to increase the pressure inside a container of gas. So what are 2 ways we can increase pressure? Yeah, so one way is we can decrease the volume. And then do y'all have another way? Oh, I didn't see, but yeah, you can increase the number of moles. Well, I'm not going to write that down because technically in a container, we don't want to like add anything to it. It's the question doesn't explicitly state it, but that's usually asking how can we like manipulate the environment of the container in order to increase the pressure in this case. So your answer, increase the number of moles, is correct, but a better answer, yeah, would be increased temperature. And the way that we can know this is by using that combined gas law. So through this combined gas law, we can see all of the relationships of pressure to volume and temperature. So are pressure and volume inversely or directly related? Yeah, inverse. So as pressure increases, volume decreases. And then what about with pressure and temperature? Are those direct or inverse? Yeah, that's a direct relationship. As pressure increases, temperature is also going to increase. So yeah, that's how we got this answer. Okay, so 13 says, at a constant temperature, a gas sample occupies a volume of 5.67 liters at a pressure of 760 mmHg. What volume would it occupy if this pressure was increased to 1,000? So which equation are we using for this problem? Yes, exactly. We're going to be using P1 V1 equals P2 V2. So what's our initial pressure? Yeah, 760 mmHg. And then what's our initial volume? .67 liters. And that's equal to, what's our final pressure? Correct, 1,000. And then we're looking for our final volume. So do the math out and let me know what y'all get. Yeah, 4.30 liters. That's the correct answer. Any questions? Okay, so we are on our last two problems. We have 14 and 15 left. So let's do 14. It says a mixture of nitrogen gas and carbon monoxide are separated by effusion. Which gas would effuse faster? So when we're talking about effusion, which one is going to effuse faster? Something with a high molar mass or a low molar mass? Yeah, so we're going to have high effusion with low mass. Okay, so we have nitrogen gas and we have carbon monoxide. What's the molar mass for nitrogen gas? Yeah, 28 grams per mole. And then what about carbon monoxide? Yeah, Carbon monoxide is also going to have a molar mass of 28 grams per mole. So this question doesn't have like a definite answer, but what can you say about the fusion rates of these two? Are they going to be, is one going to be greater than the other, or are they going to be about the same? Yeah, they're going to be about the same. Yeah. But then if we had done this problem and one of the molecules had a smaller molar mass than the other, then we would have picked the smaller molar mass to be the answer to this question, because a lighter molecule is going to fuse faster. Okay, so last question we have 15 says a gas mixture of neon and argon has a total pressure of 4 atm and contains 16 moles of gas. If the partial pressure of neon is 2.75 atm, how many moles of argon are present in the mixture? Yeah, okay, so what's the formula for partial pressure? Yeah, so that's to find the pressure of the total container, but what about finding partial pressure for individual gases in a container? Yes, correct. So we're going to have partial pressure equals the pressure of total times your mole fraction. So how are we going to approach this problem? Because we're trying to find the moles of argon, but we're given the partial pressure of neon. So what do we need to do first? Yeah, so we're going to find the moles of neon, correct. So based on this equation, we know the partial pressure of neon. What is it? Yeah, we have 2.75. And that's equal to pressure total. What is our pressure total? Yes, it's 4 atm. And then we can just solve for the mole fraction of neon. So what's our mole fraction? Yeah, 0.6875. So now we know the mole fraction of neon. From this, are we able to find the mole fraction of argon? Yeah. So remember that your mole fractions always add up to 1. In this case, we only have 2 gases in our container. So our mole fractions of neon and argon should add up to equal 1. So what's our mole fraction for argon? Yes. Yeah. So that's our mole fraction of argon. And what's our last thing that we need to do to find the moles of argon that's present? Yes, multiply by total moles. So we have 16 moles total, and argon makes up 0.3125 of those 16 moles. So treat it as like a percentage almost, and multiply them together. And what's our final answer? 5. Correct. Yeah. So that's our final answer. Do y'all have any questions? I know this one kind of seems tricky, but once you start doing it, it's not too hard. If there's no questions, then we're all out of questions. So you are free to go for tonight. Yes, I am using a tablet. Is it because it's neat? I used to use the mouse and it would be awful, but I got the tablet, so it's much better. Thank you. You're welcome. Good luck on your test. I'm sure y'all are going to do great.